Hey guys, so in this video we're going to cover how to express the equilibrium constant of a reaction that is at chemical equilibrium. So these are the two types of arrows that chemists use to designate the extent at which a chemical reaction occurs. Now this single arrow indicates that the reaction goes to completion. So theoretically that means that all reactant molecules are fully converted to product molecules. This type of reaction is irreversible. And a double arrow here symbolizes that the reaction is reversible. Now this is termed an equilibrium reaction because no extra energy is required for the products to revert back to reactants. Once the reaction has reached chemical equilibrium, the extent at which the reaction has proceeded can be measured experimentally and expressed as an equilibrium constant. So when a reaction is at chemical dynamic equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. So if we take a look at a graph of time versus concentration of a reaction that can occur in both the forward and reverse direction, so H2 plus I2 going to 2HI, but it can also go in the reverse reaction. We observe that initially the forward reaction dominates. So here if we take a look at this inset graph, the rate of the forward reaction initially is much higher than the rate of the reverse reaction. But we can see that as the reaction begins to reach equilibrium, the rate of the reverse reaction increases. Now once the system has reached this dynamic equilibrium, the concentrations of the reactants and products will remain constant. But we can see on the graph that this does not necessarily mean that the concentration of all reactant and product species are equal. But the reason that these remain constant is because the rate of the forward reaction is equal to the rate of the reverse reaction at equilibrium. Now the equilibrium constant is a way in which we can quantify the concentration of reactants and products at chemical equilibrium. So we designate the equilibrium constant with a capital K. Make sure you don't confuse this variable with a lowercase k. Remember that represents the rate constant of a reaction, and they're extremely different values because the rate constant is a measurement related to kinetics, whereas what we're talking about, the equilibrium constant, depends on thermodynamics. So this value K, the equilibrium constant, is actually expressed as the concentration of the products at equilibrium raised to their respective coefficients over the concentration of the reactants at equilibrium raised to their respective coefficients. Now I know that's a mouthful, so I think the best way to help you understand this is by showing you a generic example. So if we have the equilibrium reaction of A plus B forming C plus D and their respective coefficients of A, B, C, and D, the lowercase letters, we would express K as products over reactants raised to each of their respective coefficients. So K is going to be equal to the concentration of product D raised to its coefficient, lowercase d, times the concentration of product C raised to its coefficient, lowercase c, over the concentration of reactant A raised to its respective coefficient, lowercase a, times the concentration of reactant B raised to its respective coefficient, lowercase b. And we actually have a name for this relationship between K and the balanced chemical equation, and it's called the law of mass action. So it's important to note that when we express K for an equilibrium reaction, we do not include products or reactants that are in the solid or liquid state. We're only going to include them if they are in the gaseous or aqueous state. So whatever value we solve for K, it's going to inform us whether the forward or reverse reaction is favored at dynamic equilibrium. So say we consider a situation where K is much less than 1. So if we think about this value in terms of a fraction, because remember it's going to be products over reactants, that means that the denominator is much larger than the numerator. So that means that we have a higher reactant concentration at this certain value of K. So in other words, a small k means that the reactants are at much higher equilibrium concentration than the products. So when K is less than 1, that means that the reverse reaction which converts products to reactants, is actually going to be favored. Now, if we consider a situation where K is approximately equal to 1, this means that the numerator and denominator are roughly the same value, so that, in other words, the product concentration at equilibrium is approximately equal to the reactant concentration at equilibrium. So therefore, when K is approximately 1, neither the forward nor the reverse reaction are going to be favored. And finally, if we consider a situation where K is much greater than 1, this indicates that the numerator is going to be larger than the denominator. Remember, since this is a ratio of products over reactants, this means that the concentration of the products at equilibrium is much greater than the concentration of the reactants at equilibrium. Therefore, the formation of the products is going to be favored through the forward reaction. So overall in this video, we have learned that the equilibrium constant is a measure of the extent of a reaction governed by thermodynamics, and the value of this equilibrium constant is determined by the law of mass action and indicates if the forward or reverse reaction is favored by a chemical system at equilibrium.